My other one's just simply not projecting, and I have no idea what's wrong. It's making me mad, but I have no idea what's going on. I assume that's still recording. Because we'll find out. Oops. And I hit the wrong button. How are we doing? Pretty good.
Cold.
Cold? I know I got cold again.
I don't know how you're wearing shorts and a t-shirt.
Well, I come in. I have a pullover. I want to come in, so. But it's because this building has different temperature zones. Part of it's cold, part of it's hot, part of it's cold, part of it's hot. So that's why I always wear shorts, because I don't like being hot, and I hate jeans. I don't like wearing jeans.
Yeah, I don't either. I understand that.
So, like, any questions on anything before we do new stuff? All right. So last time we were talking about cyclic groups and finishing that stuff up. We will do a little bit more with that here today as well, as we talk about a couple of other different properties of things as we're doing things with homomorphisms and isomorphisms. And then we'll also do some things with permutation groups again. Symmetric group, alternating group, another one called alternating group, which we haven't talked about yet. But do some of that stuff today. So section 7.4. A little bit bigger. Section 7.4 talks about isomorphisms and homomorphisms for groups. It's the exact same definition that we did for rings, except that you don't have to worry about two operations. You only have to worry about one. And so literally the same concept, but it's just for one operation rather than two. So if we say we have a function phi going from G to H, where our G and H are groups, then phi is a homomorphism if the function breaks up over the operation. Well, that was really bad handwriting today. Sorry. So the important thing to remember, and we could put in operation symbols for emphasis if we wanted to, but the important thing to remember is that A and B are coming from G, so this operation that's inside the function on the left-hand side of the equation is taking place in the group G, whereas over here, this operation is taking place over in the group H, in the codomain. So when we say operation preserving, we mean we can either do the operation first in the first group, and then map it, or we can map each individual element and then do the operation, and we should get to the same spot. So that's what we mean by operation preserving. So even though we've written this multiplicatively, we need to understand that this is whatever the group operation is in G, this is whatever the group operation is in H. So if one of them is additively, then it would be a plus sign. If it's permutations, then it would be function composition. Okay? But just keep that in mind, that it's dependent on what group you're in for what operation you're doing. But again, for homomorphisms for groups, we literally only have to worry about the one operation. Okay? So like I said, we've already talked about a lot of this stuff before with rings. Rings would provided a little bit more structure because I had to preserve both addition and multiplication. Right? Pardon me. If phi is 1 to 1, same names that we gave before. If phi is 1 to 1, then we call phi a monomorphism. I just said a monomorphism was going to be a nomomorphism. Nomomorphism. If phi is onto, then phi is an epimorphism, same words. We'll talk about the last word here in a second, which you probably already know what it is. But we care about monomorphisms if we can do sometimes what we call embed one group in another. So if you have a one-to-one mapping from one group into another, then basically what we're doing is we're taking that group and thinking of it as just literally stuck inside the other group. So what I mean by that is, for example, if you do maybe the map from Z to Q, where I just map phi of n to itself, that's clearly a monomorphism. Now, it's clearly one-to-one. Let's do that first. It's clearly one-to-one. It preserves addition without any issues, right? Clearly not onto, but clearly, hopefully it's clear that it preserves addition without too much difficulty. So what we're doing is we're embedding Z inside of Q. And so we can think of Z, a copy of Z, or literally living in Q, which you think of anyway, right? And that's the idea of that embedding idea. I'm taking a copy of this and sticking it in here. You could do the same. Nothing was special about Q here. I could take phi and go from Z to polynomials with integer coefficients and do the exact same map. And then I'm just thinking of the integers as the constant polynomials. Does that make sense? So these one-to-one things, we really think about putting them one thing. I'm really thinking about just taking one thing and sticking it inside, literally an exact copy, and sticking it inside of something else. Okay. For the epimorphism, we usually say that if it's an epimorphism, if it's onto, then we say that the second group is a homomorphic image of the first group. Okay. And then if we know some things about G, and I know that H is a homomorphic image of it, then I know some things about H as well. So for example, if I know that my homomorphism is onto, and I know my domain group is abelian, then I know that my range group is also abelian. Okay, so some group properties would be preserved if I know that one group is a homomorphic image of the other. And we'll see what I'm talking about by that here in a little bit. Okay. Pardon me. All right. And then finally, if phi is one-to-one and onto, like I said, you probably already guessed what you mean by this word, that phi is an isomorphism. So just like what we did before when we were showing something is an isomorphism, if you wanted to show something is an isomorphism, first you need to make sure you have a well-defined function. And then, pardon me, it needs to be well-defined, it needs to be one-to-one, it needs to be onto, and it needs to be operation preserving. Now back with ring stuff, we had to show that both operations were preserved. For groups, we only have to show that one operation is preserved. So let's see if we can do an example or two. Let's look at, see if I can find one here that I actually want to do. But I had one picked out. Oh well. Why am I not? Okay, let's look at, this is number 4. Let's just do it this way. Number 4 has F goes from R star to R star, defined by F of X equals X cubed. So one of the reasons why I picked this particular one is the fact that I want to remind all of you about the different operations depending on what symbol we write. Okay, so remember that when we do R star, we throw out 0, right? The reason why we would like to throw out 0 from the reals, or throw out 0 from the rationals, or throw out 0 from the complexes is because 0 does not have a multiplicative inverse. So if I throw out 0, then I get a group under multiplication. So if you see R star or Q star or C star, you're assuming that the operation is multiplication that we're talking about. If the star is not there, if I'm talking about R or Q or C, then the operation is going to be addition. Because remember, for a group, every single element has to have an inverse under the operation. So I cannot use multiplication if zeros in there. Does that make sense? So, just in general, a lot of the problems that you get, they don't specify the operation. So you need to make sure you pay attention to what the operation is that we're talking about. Hopefully, it's also pretty obvious from what you know about how exponents work that if I was using addition, that exponent's not going to behave very nicely with respect to addition for operation preserving. Right? If the operation is addition, eventually I would have to see this is equal to this. Right? If the operation were addition, the first part's saying do the operation in the domain and then map it. The second one's saying map and then do the operation. Is that true? What I wrote down? Not in general, right? Works for some elements. Works in a ring of characteristic 3, but doesn't work in general. Okay. So again, we better be doing multiplication here. Otherwise, this is not going to work. Okay. All right. So this particular problem wants you to show that this really is an isomorphism. Pardon me. So again, we need to show that it's 1-to-1, it's onto, and it's operation preserving. So for 1-to-1, what do we start with for 1-to-1? So assume that we have 2 outputs that are the same, right? And then show that the inputs are the same. Okay. So if we start with f of x equals f of y, f of x is equal to, and f of y is equal to y cubed. And then to get x equals y, what are we going to do to both sides? Square root, cube root, good. So x equals y at that point. Now, would this have worked for square root, by the way? No, because when you do the square root of both sides, you get plus or minus, right? So this works for even root, or excuse me, it works for odd powers, but doesn't work for even powers. Now, you'll still get, in this case, you'll get a homomorphism every time, but you won't get an isomorphism because it won't be 1-to-1. Is that okay? All right. So f is 1-to-1. So onto, what do we do with onto? How do we start an onto proof?
You have an output to something.
Okay, so I have to start with something in my codomain, right? So I need to show that everything in the codomain is an output, right? So I need to start with a potential output and find an input that maps to it. Okay? So if we let y be in R star, then we need that to be the output of the cubing function, right? I need something cubed gives me y. So what do I need to put in? Yeah, the cube root of y, right? So cube root of y is also still a non-zero real number, and f of cube root of y is cube root of y cubed, which gives me y. So f is on too. Using a different computer today because my other one still is not communicating to project. I have no idea what the problem is. But I was checking the battery level because this is also older. I don't remember how long the battery lasts. That okay? Basically, remember for onto, you're essentially trying to solve an equation, right? You're trying to solve this and figuring out what x is in terms of y. That's what you're doing for onto. It's a solving thing, right? I have the output. I need to find the input. As a specific case of that, you do that when you try to find zeros of a function, right? You set the function equal to 0. You're trying to find the inputs that give you 0 out, right? This is just saying use any output. What do I need to put in for the input? And again, it'll be in terms of the output like it was here. Okay, so then finally, we need operation preserving. Oops. So f of xy is going to equal what? Yeah, xy, the whole thing cubed, and this is why we need multiplication, right? Rather than addition, that was what I was mentioning before, because now since I have multiplication, and since our multiplication commutes, what can I do with the cube? I can distribute it essentially, x cubed, y cubed, right? And x cubed, a different name for x cubed is what? F of x, good. And the different name for y at y cubed is f of y, good. So f is operation preserving, hence f is an isomorphism. Again, remember the word isomorphism basically means same structure, right? So even though we cubed everything, we didn't really change the structure of the group. In some sense, we just kind of stretched it out. We didn't change the structure fundamentally. When you have, you don't need to know this name, but when you have a group and you find a function that is an isomorphism from the group to itself, we call that an automorphism. Like I said, I don't really care that you remember the name because we're not going to do much with automorphisms, but basically, one of the things you can do with automorphisms is that you can create a group of automorphisms of a particular group by doing function composition and create new structures from that. Like I said, we're not going to do that, so I don't really care. All right. Anyway, is this okay about how we do? I mean, shouldn't look any different than what the stuff we've already done before, right? It's just now we get to stop because we only have one operation. So, yes.
So if the star wasn't there,
Hey, Mazana.
you would do both.
Say it again.
If the star wasn't like on ours, you would for the operation preserving, you would check the addition and multiplication, or you just check addition.
You just check addition for these because we're doing group up. Yeah. So you would need to know what you're trying to prove to start with. So it's either going to need to. It needs to be understood that you're only doing groups, so you still only have to check the one, or it needs to be understood that you have a ring and you need to check two.
Okay.
So for your exam, you'll only have to do group.
Okay.
Unless you're doing the oral part, and then it'll be ring because they'll be separated for you.
Okay.
But generally speaking, you need to know if you're talking about an isomorphism of groups or an isomorphism of rings. That's important. Sorry. As an example, let's say I have a function that goes from phi to 2z, from z to 2z, where I just do the doubling function. Without going through all of the details, you should be able to show that this is 1 to 1 and on to. It will preserve addition, because the 2 will distribute over addition, but it will not preserve multiplication. Because if you did phi of mn, that would be 2mn, but phi of n is 4mn. It does not preserve multiplication. So the group of integers is isomorphic to the group of even integers, but the ring of integers is not isomorphic to the ring of even integers. So addition will get preserved, but multiplication will not. So this is why I said it's important to know the context, right? Because if I asked you to show that this is an isomorphism, I have to be talking about some, because they're not isomorphic as rings. Okay. Another thing that tells you that they might be isomorphic to each other, we talked about cyclic groups last time. What generates Z again? What generates all of Z? What can you use to generate all of Z? 1. What generates all the evens? 2. Yeah, because I can add 2 to itself over and over again, or subtract 2 from itself over and over again, and I generate all the evens, right? So both groups are cyclic. They're both infinite cyclic groups, and they're isomorphic to each other then. Okay. So, in any event, this is why I was mentioning that. And that was a very good question you asked. It's important to know what we're talking about, whether they're isomorphic or not. Okay. All right, let's do another one. Let's look at number 5. Say we have phi goes from Z9 to Z9, where phi of x is 2x. The operation preserving part here is not difficult. Hopefully it's not difficult. Let's do that first. When we're talking about Z mod n groups, and again, I'm using the word group. When I'm talking about Z mod n groups, the operation is addition. We're assuming the operation is addition. So I'm going to do phi of x plus y here. Okay. What is phi of x plus y equal to in this case? Okay, 2 times x plus y, good. And then what can we do with the 2? Distribute, good. And another name for 2x is, and another name for 2y is phi of y, good. So notice this works for operation preserving for sums, but it would not again work for operation preserving for rings because it would not preserve multiplication. We talked about this before back when we did operation preserving for rings. If we have something that's just a multiple of an element, this thing needs to be an idempotent in the output. Remember, idempotent is something that squares to itself. So you get that operation preserving for multiplication part. We talked about that before. Good news is we don't have to worry about it now. Yay. Okay. All right. So let's do 1-to-1, and then hopefully we can help to figure out what by 1-to-1 to help us get onto. So again, to start with, for any 1-to-1 proof, we need to start with assuming 2 outputs are the same and conclude that we get 2 inputs are the same. This one's going to get a little bit strange. Well, yeah, it'll get a little bit strange. Because, again, we're talking in the group Z9 as the operations under addition. But I need to use something about the multiplication that we know we can also define on Z9 to be able to get this to be 1-to-1. Okay, so if this were just integers or rationals or reals, what would you do with the 2's? Divide them out, right? That's the same thing that we want to do here. We want to be able to divide them out. The issue is that I'm in Z9, not in a structure that we necessarily can divide in, right? But however, there are elements that we can divide by under multiplication. We refer to those as what again? The ones that have multiplicative inverses are called units. Good. So some things have the units in Z mod n groups. How do you know if something is a unit or not in the Z mod n's? What has to be true about the element if it's going to be a unit in Z mod n?
You can get to any item in the group with it.
True. As a structure thing, you're right. I think I know what you're saying, and yes, that's right. I was looking for something a little bit more straightforward. You're exactly right, what you said. What's true about the relationship between the number you're multiplying by there, or the number I'm talking about, and the n? What has to be true about the relationship of those 2 things in order for that element to be a unit?
Relatively prime.
There's the words. Yep, relatively prime, right? If their GCD is 1, then I can get the unit, right? Okay. So remember again, the reason why that works is because if they're relatively prime, you get a linear combination that gives me the identity 1, right? Mod out by the n, that goes away, and then that piece is the unit, or the multiplicative inverse that you need, right? Okay. So looking back over here, is 2 relatively prime to 9? Yes. So what do I need to multiply 2 by to make the 2 go away, essentially? Essentially divide by 2. What do we need to multiply by to, in essence, divide by the 2? What can we multiply both sides by? Well, that'll make everything go away. If I multiply both sides by 9, it'll be 0. Then, yeah, 5 will work, right? Because multiply by 5, I get 10. 10 mod 9 is 1, right? So if we multiply both sides by 5, I get x equals y in that case, because we're doing mod 9. Good. Does that make sense? All right. So then, really we're doing equivalence classes. When you multiply your 5 times 2, you get 10, but 10 mod 9 is 1. So just doing a little bit quicker through that. Do the onto. again, onto, I need to start with something in the codomain and find an input that maps to it. Bless you. And I said I wanted to do it with our discussion of one-to-one. Hopefully this will help you figure out what you need to use in order to get your input. Now let's go back to the first problem we did. Over here, why did we use cube root of y? What does it do?
You cube it, you get that.
Yeah, exactly. So the cube root of y the cube root ended up canceling out with the cube, right? When I put an input into phi, what do I do to the input? Multiply it by the 2. So I need something that's going to undo the multiplication by 2, right? What did we just say that undoes multiplication by 2? 5, right? So if I want to end up with y when we're done, what do I need to put in here? 5y. Good. Exactly. 5y. That's exactly right. So I'm going to undo that multiplication by 2. Multiplication by 5 undoes multiplication by 2. That sounds really weird. Right? But in this structure, multiplication by 5 undoes multiplication by 2. So we use 5y for the input and get y for the output. So one last thing I should state above this. This needs to be in Z9, which it is, right? Because I just would mod it by 9 if I needed to. So I would write then 5y is in Z9 and then have the rest of it. Since we showed that it's one-to-one onto an operation preserving, we really do have an isomorphism. Does that make sense? Okay. Pardon me. All right. So again, isomorphism, the idea behind the word even is that isomorphism, it means same structure, right? So you should be able to tell if things are not isomorphic if there's one property one group has that the other one does not, okay? Because again, we've got this one-to-one onto an operation preserving mapping that goes from one group to the other if they are isomorphic, right? So, pardon me. Goodness. I don't know where that came from. So, for example, if I ask you something like, why is Z8 not isomorphic to, remember your unit groups. When you write U8, this means the group of units of Z8. Oops. So if you got U of an integer, it means the things that are units in that Z mod 8 or Z mod n. Well, how many elements does Z8 have in it? 8. How many multiplicative units are there in Z mod 8? Again, what does it have to be true if it's a unit? It has to be relatively prime, right? So how many multiplicative units are there? You were right. 4, right? Remember that the order of UN is that Euler phi function of n, right? So we've talked about how we can compute that. But in particular, if it's a prime power, which 8 is, it would be 2 cubed minus 2 squared. So we get 4. Okay. So Z8 has 8 elements. U8 has 4 elements. Can they be isomorphic? And can you have the same structure if you don't have the same size? No. Okay. So the reason for this one is that the order of Z8 is 8, and the order of U8 is 4. What if I asked you, why is Z8 not isomorphic to D4? Does the order argument work here for not isomorphic? Z8 has 8 elements. How many elements does D4 have in it? 8, right? So the order thing isn't going to work here, right? But what's true about Z8 that's not true about D4? Can you tell me a property that Z8 has that D4 does not? What was our operation in D4 again? We've all slept since then. What was the operation in D4? Let me ask a better question. What is D4 again?
When I answered that question, I thought it was the rotation or the rotation groups of a square.
Yeah, rotation. Yeah, it's the symmetries of a square. What's the operation? So you have different ones, right? One's a rotation, you have a reflection. So how do you operate two different things together? What do you do?
Multiplication.
It's not quite multiplication.
Addition.
It's not addition.
Function composition.
There it is. It's function composition, right? Is that what you said?
Yeah.
Yeah, I just didn't hear you. I heard you say something. I just didn't hear you. You gotta yell it out at me.
Sorry. I will next time.
Yeah. All right. So it's function composition, right? You do one after the other. Now, why did we go through and create that operation table for D4? What was one of the things I told you to notice about the operation table for D4 way back when we talked about it? What did we notice about the operation itself? Versus something that you would know about the operation for Z8. Kind of a basic thing. Think matrix multiplication. There's something that's it's not commutative, right? The operation doesn't work. When you do function composition, typically it matters which one you do first, right? And we did that when we made that operation table for D4, didn't we? If you do the rotation, then a reflection, and then go the other way, unless it was a 180-degree rotation, you got a different answer, right? Or a no-degree rotation. Okay. All right, so this reason would be Z8 is abelian, and D4 is not. Let's do another one. This one requires a little bit more work. Why is Z12 not isomorphic? This leads me into something else I want to talk about today. To Z2 cross Z6. This one's a little bit more challenging because we haven't really talked about it yet. But let's see if we can think through it. Pardon me. Does the order argument work? How many elements are there in Z12? 12. Good. How many elements are there in Z2 cross Z6? Also 12. Good. So that order argument doesn't work. They have the same size. Does the abelian argument work? Is Z12 abelian? Yes. Is Z2 cross Z6 abelian? Yes, because each component is, right? So that argument also doesn't work. Okay. Again, we're looking for properties that one group has that the other group doesn't. Okay. What kind of group is Z12? We finished up talking about this last time. We spent a whole bunch of time talking about cyclic groups, right? What are all the Zn groups generated by for certain? 1, right? Because you can add 1 to itself over and over again and get through the whole group, right? So every single Zn group is, pardon me, every single Zn group is cyclic. In particular, then, what would the order of the element 1 be? 12, right? Because you have to add it to itself 12 times to get back to 0, correct? Okay. So Z12 has an element of order 12. Okay. What about Z2 cross Z6? And we talked about this last time as well. In a cyclic group, what has to be true about the order of an element? It has to, relative to the group, the size of the group, what does the order of an element have to do? Or it could, well, it definitely has to be less, but even better than less. Has to, so let me ask you this. Is 5 a possible order for in Z12, for example?
Oh, no, it's divided.
It has to divide it, right? We remember we had to divide the order of the group. The order of the element has to divide the order of the group. By the way, that's true in general. We'll prove that next week. But for cyclic groups, we already know that. The order of an element has to divide the order of the group, okay? So what are your possible orders for elements in Z2? 1 and 2, right? That divides 1, that divides 2. How about for Z6?
6, 3, 2, 1.
6, 3, 2, 1. Cool. All right. So if I have an A comma B, the order of this one is 1 or 2 for the orders, right? I'm talking about orders here when I'm labeling this. This is 1, 2, 3, or 6. I'm not talking about putting the elements in there. I'm talking about the orders of those elements, right? What would be the largest number? Well, that's not quite how I wanted to ask that. What would be the largest possible order, or instead of the other way around, what's the smallest number of, not smallest, I'm trying to ask the right word. If I operate this element with itself this many times, what number can I use to guarantee that I will definitely get back to 0, 0? If I want to operate that element with itself this many times, what's the smallest number I can use to guarantee that I will always get back to 0 no matter what element I choose? I'm looking for the number of times I'm operating it with itself. So 1, 1 is a good guess for what I'm talking to illustrate about it, but I want the number that I would use. So what I mean is, no matter what I put in for A, what's the smallest number you could use here to guarantee that if I operate that with itself that many times, I would always get back to 0? A 2, because it's order 1 or 2, right? For this element, what number can I use? 6. That will guarantee that no matter what I put in here, it'll work, right? So now overall, if I know it takes 2 times to get this one back to 0 and 6 times to get this back to 0, if I want to make sure they both get back to 0 at the same time, what number would I use? 6. How'd you come up with 6?
It's 2 divided 6.
2 divided 6, right? Cool. So I know that the order of this, no matter what, is less than or equal to 6. No matter what element I choose. The reason for that, I want to write it multiplicatively even though these things are additive, if I do AB to the 6th power, well, the operation in direct product is do the operation in each component, correct? We know that A squared is certainly zero, the identity. And if I raise the identity to any power, I'll get the identity, right? So this will be whatever the identity is in this case. All right. If you have a cyclic group of order 12, then you have to have an element of order 12. In general, if you have a cyclic group of order n, you have to have an element of order n. You have to have an element that is the same, an element that has the same order as the entire group. Does Z2 cross Z6 have an element of order 12? What did we just say the largest order was? 6. So does it have an element of order 12? No. So Z2 cross Z6 has no elements of order 12. In general, if AB is in a direct product, then the order of AB is the least common multiple of the order of A and the order of B. Rather than writing out a formal proof, let's just talk about why this has to be the case. If I raise AB to a power and get the identity, then I raise A to that power, I get the identity. I raise B to that same power, I get the identity. That means that power has to be a multiple of the order of A and a multiple of the order of B. So it's a common multiple, right? And then the least common multiple will work, so that's why it has to be the least common multiple. So, tell me if you know what the conclusion to this theorem is. A direct product of Zm and Zn is cyclic if and only if what's going to have to be true?
N divides N or N divides M.
So I have that case up here and I didn't get a cyclic group. Right? Because 2 divides 6. Z2 cross Z6 has 12 elements, but I have no element of order 12.
Oh.
Let me ask some leading questions. How many elements does Zm mod Zm cross Zn have? M times n. If it's going to be cyclic, I have to find an element of order M times n. What did we just say the order of an element of direct product is? Least common multiple of these two things. So I need the least common multiple to be the multiple. There we go. It's relatively prime. There we go. That's right. Yep. This is cyclic if and only if those two things are the Zm and the Zn are relatively prime. That's right. So to get this to be cyclic, I need to use an element of order M from here, an element from order N here. when I multiply, when I put them together as an ordered pair, I need it to have order mn. We know that the order is least common multiple. Well, the only way the least common multiple can be equal to mn is if the GCD is 1. And then in that case, you can always use 1, 1 for the generator. 1 generates ZM, 1 generates ZN, 1, 1 will generate absolutely everything as long as they're relatively prime to each other, the M and the N are. So, if I ask you those kinds of things now, it gives you a little bit of information about how to determine if two groups are isomorphic or not. So I can imagine an exam question that says, tell me why this group's not isomorphic to this group. Tell me why this group's not isomorphic to this group. And go along. And it's just literally, this group has this property, this group does not. That's all I'm looking for. Short little explanation of why. It tests a couple of things. It tests, do you know what isomorphism means? And it also tests some of the other words, right? Do you know how to find order? Do you know how to find what abelian means? Those kinds of things. Okay. All right, let's do a couple of proofs of some properties that any homomorphism has to be. This is theorem 7.20 in your book. We're going to let, it uses F, I hate using F. Phi going from G to H is a homomorphism. Oops. If it's a group homomorphism, then the homomorphism must map the identity of the group G to the identity of the group H. Remember, for rings, that was not necessarily true for the multiplicative identity, right? The multiplicative identity just had to get mapped to what the multiplicative identity would be for the image, but not necessarily for the ring you're mapping into. However, we did show that in ring homomorphisms, 0 got mapped to 0, right? We did show that for rings. F of 0, phi of 0 is 0, right? Well, 0, we used 0 for the additive identity, or for the group part of the ring. So this is just the same statement, that basically 0 gets mapped to 0. We're just doing it generally for identities of other groups that we may not call the identity element 0. Okay. It's the same proof. I can write the identity as the identity operated with itself, and then we have operation preserving. So I can break it up over the operation. Now we are in a group. These are elements in H. In particular, we are in a group. Every single element in a group has to have an inverse with respect to the group operation. So the inverse of the element we're calling f of EG has an inverse. Okay? So multiply both sides, or operate both sides, by the inverse of that element. I really should have some parentheses around the right side there, but we know that everything here is an associative as well. These two cancel each other out, but they're canceling each other out in H, not in G. So this is the identity in H. Same thing's true over here. And then when I operate the identity with f of EG, I just get f of EG again. This looks, hopefully this looks exactly like the proof you did for f of 0 equals 0. Because you wrote 0 as 0 plus 0 and then split it up over the sum and then subtract, right? Isn't that what we did before for the f of 0 equals 0? Okay. What's another one? Well, why am I using F's again, darn it? You look at the book and saw F again. Sorry. That should be the same name as whatever the homomorphism ones. Good grief. Sorry.
Okay. You write the F sloppily enough.
I do write the F slot. It looks the same thing, doesn't it? It's squiggle of joke about Dr. Ross limit signs in calculus. It looks like it's Arabic because he's just like it does look Arabic at that point. That's how he writes limit every time.
I know exactly what you're talking about.
Oh, yeah, okay. I was like, I don't know why my head went to summation. I was like, that's a strange looking
Summation sign? Yeah, but that would be a strange looking summation sign.
That checks out.
All right. So this one says that if you do the inverse of an element and then map it with the and then again, this doesn't have to be isomorphism. This is just homomorphism. Do the inverse and then map it. It's the same thing as mapping it and then do the inverse. So the idea here is that start with what we just proved in the first part. We know that's true from the first part. Using the element little g, what can I replace EG with? Using the element little g, what can we replace EG with inside the F?
G times inverse of G.
Good. And again, no issues here. Again, we're talking about groups. So absolutely everything in a group has an inverse with respect to the group operation. What can we do on the left-hand side of that equation now since we know we have a homomorphism? What can we do on the left-hand side? We have a homomorphism. I gotta do one more thing before I do that. You're right. I now have a group operation on the inside. What can I do with the homomorphism now with respect to that?
Split it up.
Split it up. There we go. Yep, I need to split it up first. And then which thing do you want to do the inverse of and apply it to both sides? Or operate it with both sides on? Just thinking about what we're trying to prove. Yeah, f of g, right? Operate f of g, the whole thing inverse on both sides, and move it to the other side, and you get what you want. Does that make sense? Okay. Oops. We can also talk about kernels. Remember, kernel for a ring homomorphism was the set of everything that got mapped to the 0 of the codomain, right? Remember that? Okay. So same idea for groups. It's just that the 0 is really what we mean by the group identity, correct? So this is the set of all G in capital G such that phi of G is the identity in age. And I know I've changed back to phi again because I prefer it. I prefer it so much that every time I see an F in the book, I just start writing F again. My mind is easily influenced, apparently. All right. The theorem here is the kernel of phi is a subgroup of G. So this is a good little review about how we show something as a subgroup. We've got both the one-step and the two-step subgroup test. Ordinarily, though, you end up doing the two-step subgroup test anyway to show the one-step subgroup test. So we might as well just do the two-step and call it good. So remember, even though we call it two-step subgroup test, there's really 3 steps. One is that we have to show that it's non-empty, right? We need to make sure we have a non-empty subset of the group we're talking about. And then show that it's closed under the operation and closed under inverses. Those are the 2 steps, right? Take 2 things in the subgroup, it's back in the subgroup again. Take something in the subgroup, its inverse is back in there again. Okay? So first, why is the kernel of phi not empty? By using what we just talked about in the previous theorem, what do we know is always going to be in the kernel of any homomorphism? Well, in general, we call it not 0, but the identity of the group, right? Yeah, so since the identity is always in there. Always. Okay? So now let A and B, or G and A, whatever you want to call them, doesn't matter. Give them names. Give them funny names if you want to. I don't care. It makes it more entertaining to read it. Let A and B be in there. I need to show that AB is back in there again, and A inverse is back in there again. Right? I need to show that it's closed under products, closed under the group operation, closed under inverses. Okay? The defining characteristic for being in the kernel is that when you apply the function, you get the identity, right? That's the defining characteristic. I want to show that phi of AB is the identity. What do we do first, do you think? Split it, good. Got to keep them separated. Exactly. Yep, that was a joke I made probably 12 years ago about the same thing. Gotta keep them separated. Mm-hmm.
The second you said that, I really said that in my head.
Great. All right. Now, where are we saying that A and B live? In the kernel. To be in the kernel, what does that mean? What happens when you plug it into the function? You get the identity. So we get the identity operated with the identity, which is certainly the identity. So AB is back in the kernel. We also need to show that it's closed under inverses. Again, using the theorem we just proved before we started doing this. What can I do with the inverse? Move it to the outside. Good. And what do we know phi of A is? Identity. And when you do the inverse of the identity, you get the identity. Yeah. So A inverse is back in the kernel. Hence, kernel of phi is a subgroup of G by the two-step subgroup test. The Texas two-step subgroup test. Every time in my head is what I think when I say it.
See, earlier when you said three-step, I was thinking Leonard Skinner.
Oh, nice. Excellent. I'm glad people's brains do different connections like mine do. It does. Which is bizarre. All right, that's okay? All right, so the kernel again is a subgroup. Like we talked about before, we had this theorem. You should think about how the proof of this one would go because it's the same as what we did for rings. A homomorphism is injective. A homomorphism is one-to-one if and only if the kernel of that homomorphism is simply just the identity. The forward direction, if it's one-to-one, then the kernel is just the identity makes sense because one-to-one means every input gets distinct inputs give you distinct outputs. We know the output of the identity is the identity, and nothing else can then have an output of the identity. So left to right is pretty straightforward. Right to left is the one you would not want to think about, but it's not too bad. It's pretty short proof. So think about how that one would work. That's a good one to think about. Another theorem, this is actually, according to the book, part 3 of the theorem we were doing before, but I'll just write it this way. The image of any homomorphism, I think we used F before, but that's okay, is a subgroup of the codomain. So remember again, by definition, your image is the set of all outputs. Sometimes we call that the homomorphic image of G because it's an image under the homomorphism. And again, like I mentioned before, there are some properties that are preserved under a homomorphic image. For example, abelian would be one of those properties that's preserved by homomorphic image. So again, if I want to show that this is a subgroup, we'll do two-step again. Of course, to be able to do that at all, you still have to show that it's non-empty. But certainly, it's not empty because if I map the identity over, I always land on the identity. So the identity has to be in here, right? So we see E sub H, which is phi of E sub G, is in the image. So now I'll call them X and Y now in the image. We need to show that XY is back in the image and X inverse is back in the image. We have to show that it's closed under the operation, closed under inverses, right? Right. So what does it mean to be in the image? Well, in the image, there has to be something in the domain that maps to it, right? Do you agree? Okay. So then there exist, what names do you want to give the two elements? I need two names. A and B, okay? Such that phi of A equals X, and phi of B equals Y. One semester I had students trying to give me all sorts of different pictures to try to draw. It was rather amusing. So there were, what's that?
Do it all in
Do it all in wingdings. I had that happen one semester. I was teaching a history and math class, and so I was using PowerPoint slides since some of the information was just more, here's information rather than going through math stuff, right? So I had slides to go through. Well, I had math symbols in the slides, but I didn't embed this is a long time ago, but if you put math symbols in the slides, apparently if you moved from one computer to another, you needed to make sure you actually embedded the fonts you were using into the slides before you saved it and then moved to another computer. So I went from one computer to the next. Oh, hell, there was wingdings everywhere on the screen. Like, there was pointing fingers and all sorts of weird stuff just everywhere. Like, well, this is interesting. The students thought it was hilarious, of course, but like trying to explain what I meant by all those things was really kind of funny.
pretty good.
It was pretty amusing. It would have taken a lot of effort to actually try to do that on purpose, so it was rather comical. All right. Remember again, we want to show that XY is in the image. So what element in G do you think we should use to map to the element XY? AB, good. So to get to that point, if I do phi of AB, what should we do first? Split it. Phi of A is, and phi of B is Y. So we have XY is in the image, right? There's something mapped to it. We also need to show that X inverse is in the image. What element do you think is a good candidate to map to X inverse? A inverse, right? What can I do with the inverse? Move it to the outside. Then we get X inverse when we're done. So hence XY and X inverse are in the image. And the image of phi is a subgroup of H. Is that okay? One of the things that you can do, and we're not going to do it because we're not going to use it later, and I don't want to spend the time improving it. Remember we talked about the symmetric groups? Those are those, and we're going to talk a little bit more about those properties next time, or play around with the symmetric groups a little bit more next time. I thought we'd get to some of it today. We've already played around with it a little bit. We're just going to formalize a couple of more things with symmetric groups and then move on to the last thing that we'll talk about this semester. But one of the things that you can do with this homomorphic and isomorphic ideas is that you can show that every single group, no matter what group you're talking about, you can always embed it in some permutation group. Remember, permutations are just functions that are one-to-one and onto functions from a set to itself. So all the SNs are permutation groups. No matter what group you're talking about, you can always embed it into any symmetric or permutation group. What that means is that everything basically lives in these permutation groups, and so every finite group would live in every single permutation group. So a lot of things that you can talk about as far as proving things, if you can do them for the permutation groups, have to hold for all groups. It's referred to as Cayley's theorem. Like I said, we're not going to use it, so I'm not going to worry about proving it. That's also just at the end of this section. But it's nice to know that I can really talk about getting every single group, no matter what, in the same language, right? We've talked about different types of group. We talked about doing groups modulo an integer under addition. We've talked about multiplication groups modulo an integer and being relatively prime to that integer under multiplication. We've talked about groups that are function composition. We've talked about them all in all sorts of different contexts. What's nice is that we can really move everything into the same context, which makes a little bit things from a language perspective simpler. That's what Cayley's theorem does. Okay. That's all I'm going to talk about, Cayley's theorem. Okay. So next time, we'll get into playing around with those permutation things. In particular, I just want to play around with that cycle notation more that we've already talked about. Talk about some of those properties. Talk about orders of elements in those properties. And then the last thing we'll talk about, go back to cosets that we talked about with rings. And I want to get to the point where we can show that the order of any subgroup actually has to divide the order of the group. Okay, so that's what we want to get to end things on. So we'll do that next week. All right. Have a good one. And we'll see you next week.